Hello and welcome to our next set of notes. We are on Unit 2, we're on section 7.2. So this is actually our last section of Chapter 7. The first section, so the last video you hopefully watched, we learned about estimating population proportions. So we were dealing with percentages or proportions and trying to build that confidence interval. We took our point estimate, which is the value we got from our sample data, and then used our margin of error to make some window or wiggle room around it, and then found these two outlying values, which would be the ends of our confidence interval. We're going to be doing basically the same thing this section. We're going to be dealing with means now instead of proportions. That's going to be the big difference. So in this case, we're dealing with the average or the mean instead of looking at percentage or proportion. So our point estimate for these problems, our point estimate, the value we get from our sample is going to be the sample mean. So the point estimate is the sample mean x bar. So that's going to be our estimate. So from your sample data, you'll find an average for your sample data, and you use that as an estimate for the population mean, or mu. So you're kind of trying to infer about what mu is, what the average for the entire population is. So use your sample value as an estimate for that value. We will construct a confidence interval, just like we were doing the previous time. To do the confidence interval, we're going to find those critical values like we did before. The critical values cut off the not significant to the high and low significant stuff. And then we use the critical value to make the margin of error. So the margin of error is kind of, I call it the wiggle room. It's how much spread we need around the sample mean, the point estimate, to make the confidence interval. And so then we'll use that point estimate and the margin of error to get the endpoints of the confidence interval. So remember, the point estimate is going to be in the middle of the interval, and then you'll add subtract the margin of error to get the endpoints. So a lot of this will be very similar. Now, a few things will be different. One thing is the requirements. So we were doing the last section, we just had those requirements about binomial distribution, normal, and then the whole successes and failures being at least 5. Well, the requirements for the means are a little different. What we're going to really require is normality. We said, based on the central limit theorem we learned about in Chapter 6, that anything of size 30 or larger meets our sample requirement and is going to work. It doesn't matter how normal the set of data is, because if your sample is big enough, bigger than 30 or larger, then you're going to be good to go. But there actually is a way to work with samples that are smaller. You can work with samples in the 15 to 30 range as long as it appears to be normal. So like if you do a normal quantile plot and you graph it, or you do a histogram and you draw it, and it looks normal, and there are no outliers, which means if you do the box plot with the outliers, nothing shows up. So you can work with small samples between 15 to 30, as long as that's true. If your sample falls below 15, then we're not going to really use these methods like in techniques. That's another thing we'll say for an advanced statistics course. For us, we'll just always pick something 15 or bigger. And if it's in the 15 to 30 range, as long as it looks normal and there's no outliers, you're good to go. If it's bigger than 30, you can use whatever data you want as long as your sample size is bigger than 30. So let's just look at a couple examples and decide if these would actually follow the requirements we need. So first off, we have a sample of 45. It says it's right skewed and there's no outliers, but that doesn't really matter because our sample is really big, right? Sample 45. So 45, that's bigger than 30. And that's all we have to check. As long as your sample is bigger than 30, sample n is bigger than 30, we're good to go. Large sample always works. And I know 45 doesn't sound that long or large, but as long as it's bigger than 30, it's a big enough sample. Next thing, sample of 22 students. So notice this one, it's not bigger than 30 anymore, right? So we don't have that bigger than 30. So this one, 22, is actually less than 30, but it is bigger than 15. So far that's okay. We're okay as long as we're between 15 and 30 if it's normal and no outliers. It does say it's roughly normal, so it is roughly normal, and that's good. So far so good. We got between 15 and 30, roughly normal. But then we go to the last thing we see that has an outlier. So in this case, there's outliers, so it doesn't work. Because what we said, only can work with small sets of data if there's no outliers. So it has outlier. So, this one is not useful. No, cannot be used. Okay, last set. 18 people, it's still between 30 and 15. So as long as we satisfy the requirements of being roughly normal and not having outliers, we're okay. It is roughly normal. So again, as long as we have that and no outliers, we're good. It's roughly normal, and there are no outliers, so it has no outliers. So it meets all the requirements. Even though it's less than 30, it's between 15 and 30, and it's roughly normal and no outliers. So yes, can be used. So this is something that every statistician does when they're working with the data. They either get a sample bigger than 30, so they're just good to go because their sample is large enough, and so it can be used. Or if they have to work with a small set, and sometimes you have to. Sometimes there's not many people that satisfy whatever requirements. If you're trying to like study a rare disease or something, there might not be that many people that you can survey. And so if you get below 30, you watch out for things like, okay, is my data what I got normal, and does it have outliers? And if neither of those are, if it's roughly normal and there's no outliers, then you're good to go, even though you had a small data set. Okay, so that's one thing. The check requirement is a little different. Again, sample size, as long as you have a big enough sample, you're good to go. But if you have a small sample, you look for these other things. Second thing that is very different, and this is specifically because most of the time when you work with means, you don't know the spread or the standard deviation. You don't get to work with the standard normal curves, the z-curves. So when you're working with population means, with averages, you're usually required to work with the population standard deviation, but a lot of times you don't know it. So this is pretty typical. Pretty typically, the standard deviation sigma is not known when you're working with trying to figure out the population mean. So you're trying to work with mu, the population mean, and you don't know sigma, the standard deviation. When you don't know that, you will use the sample standard deviation instead. So we'll use the sample standard deviation, which is S, right? That's the letter for sample standard deviation. And you'll use that as an estimate for the population value. So you're going to use the spread of your data that's in your sample as an estimate for the spread of all the data in the whole population. Since it's only an estimate, it ends up so that you can't quite standardize. You can't get a good standard normal curve. So what instead you have to do is you have to use the student t-distribution. So this is a different curve. It's like the normal distribution. It's a bell curve and all that. But the normal curve, so this chart shows here, the normal curve is this really the highest one. It's got the least variation. The t-curves, there's actually multiples of them, will all have more spread. Because they're wider, not taller, they're going to end up more spread. So the t-distributions, the t-curves, have more spread, which means they don't work quite as nicely as the standard distribution. T-curves have more spread. There are lots of them. We'll talk about why in a second. So the values along the t-distribution are called t-scores instead of z-scores. We have the z-scores and now we have t-scores. So those are two big things. You work with t-scores when you're working with means. You saw in the previous section, chapter 7.2, that we worked with z-scores, and that's always true for proportions. So that's one way you can kind of tell. If you're working with proportions and you're doing like the confidence intervals, you get to work with the z-scores. If you're working with means and you're doing confidence intervals, you're typically going to have to work with t-distributions. Okay, so we call these the t-distribution, we call these t-scores. They're like z-scores. You kind of standardize, but again, it's a little different because we don't know the population standard deviation. And so this is the formula, and it kind of should be a little similar. So if you see like the mean, the sample mean minus the mean, so we're subtracting the mean. And on the bottom, this looks weird, but if you think about that as the standard deviation tweaked by the sample size, because remember we did that earlier where we had the sample size and we took the standard deviation divided by the square root of the sample size. So this is kind of similar, a little bit of thing. That's the calculation for how they find t-scores. And so you notice they'll have to know the sample mean. They have an estimate usually for what they think the population mean is. We're using their sample standard deviation and the sample size. But if you use those values, you can calculate what's called a t-score. Now, t-scores depend on the sample size, right? So as the sample size changes, the t-score changes. So there's actually lots of different t-distributions. To help us out when we make charts of these t-distributions and stuff, we label them by what we call their degrees of freedom. So the degrees of freedom, just a fancy name for us, is basically the sample size, just kind of really similar to the sample size. The degree of freedom is always just one less than the sample size. So if you survey 30 people, the degrees of freedom will be 29. That's really what we'll do with it, basically. Degrees of freedom is pretty easy to figure out because there's always one less than the sample size. So the t-curve you work with will depend on your degrees of freedom. So like this one, degrees of freedom are 1. So they actually had a sample of 2, a really small sample, which we wouldn't really deal with, but that's why it's got a lot of variation. It's a very short curve because it's really spread out. So not very good. The degrees of freedom for the 6th one, well, this one is like a sample of 7. It's going to be closer to the standard normal curve. In fact, it is a rule. As your sample size goes up, the t-distribution gets closer and closer to the z-distribution. So if you get a really big sample, you're going to get really close to like having like regular z-scores. So as sample size increases, the t-distribution gets closer to the z-distribution. A couple other things, we did say it is similar bell shape, so it's got similar bell shape, but it has more variability. So it's more spread out. It is centered at 0, just like the z-score. There's a middle 0, just like the z-scores. And the mean or the average does have a t-score of 0, just like the mean has a z-score of 0. Standard deviation varies with sample size, but it's always going to be bigger than 1. The standard deviation varies, but it's greater than 1 always, because we're always more spread out than the standard normal curve. Remember, the standard normal curve has that standard deviation of 1. So that's going to be a little different for these t-scores. That's really just kind of get you an idea about the t-scores. We'll see that most of the time we don't have to worry too much about all that stuff. It is nice to know they look a lot like the standard normal distribution with a 0 in the middle. They're symmetric. It is symmetric, just like the z-score. And again, just really be careful about the degrees of freedom. That's probably the most important thing on this page is remember the degrees of freedom for your t-scores is always 1 less than the sample size. So let's go ahead and find some t-scores just so we can get familiar with them. So I'm going to give you areas and ask you to find the corresponding t-scores. That's the first thing we're going to do. We use areas and find t-scores. So first off, we want to find the t-score that has an area of 5% to the left. So that's to the left, area of 5%. And then they give us the sample size. Now, why do they give us the sample size? Well, because you need to know that the degrees of freedom is the sample size minus 1. So this is, the sample size 12 is telling us that the degrees of freedom is 12 minus 1, or 11. So they actually just gave us the degrees of freedom. That's what they're giving us when they give us the sample size. Okay, if I look at a t-distribution, it's going to look a lot like my z-distribution, a little curve like this. Remember that we have 0 is in the middle, so that's the middle. We want an area of 5% to the left. So if I think about this, remember 0 has 50% to the side. So if I want 5%, I'm going to have to like go over here, right? So this area right here can be 5% or 0.05, right? Because that's 5%. And then over here, thing will also be above that. And they want the t-score that goes right there. What's the t-value? It has 5% to the left. Now to do this, one way to do it is with a t-chart. And there is a t-chart. This will be provided with this Unit 2 exam. So you'll see we have a couple charts, the z-chart and the t-chart. This one has a different way of looking at it. First off, you notice that it has the areas up here in the top, and then also on the bottom if you look from the bottom. So if you get close to the bottom, it's easier down here. But you can see the areas. And it has areas for one tail and areas for two tails. So you got to pay attention to which one you're using. In this case, we're just looking at one tail. There's nothing over here on this other tail. We're just looking at one tail. So we would use 0.05 and one tail. So that's the column we're going to look at. Now, why is there a whole bunch of numbers? Well, because it depends on the degrees of freedom. So since we said the degrees of freedom are 11, we're going to look down here until we find the degrees of freedom are 11, and then match that up with one tail, 0.05, and we'll get the corresponding z-score. So a z-score of 1.796, when we have degrees of freedom 11, and there's an area of 0.05 in the tail. So again, the areas up here, these are your z-scores in the middle. You notice these z-scores are all mostly between 3 and -3. There's some that are further out because these get a little bit further out, especially when you have small degrees of freedom. But as your degrees of freedom get bigger, these always be kind of between 3 and -3, like z-scores. So yeah, this one ends up being 1.796, which is a good in between -3 and 3 number, because we always saw z-scores between -3 and 3. And again, degrees of freedom 11, area and one tail is 0.05. That's how we got 1.796. So from the chart or the table, the t-score is 1.796. It's because we use this for our area, use this for our degrees of freedom, and from that we got the answer, 1.796. Now, I almost made a mistake here. I hope you caught it. Notice this t-score is positive. but this t-score is supposed to be below 0. That doesn't work, right? We can't get a positive number on this side because we saw on the chart on the previous page that even with the t-scores, the left side is the negative values and the right side is the positive values. Well, you got to be careful here because this area, this chart, only gives you the positive numbers. It's not really working left or right and negative positive. It's only giving positive values. So you see, this is all positive. They don't have a negative side for this chart. So you do have to watch and note that this has to be negative because it's less than 0. So we actually want to turn this into a negative number to get the right value. We actually found 0.05 to the right is what we did. But since we want 0.05 to the left, we definitely knew we wanted to have a negative value, so this should have been negative 1.796. So you can see how this would be really easy to mess up and get the wrong sign if you're not drawing your little picture and thinking about where you're at. You know, think about you're on the left side, you need a negative number for your answer. Okay, let's try another one. Let's try a different one. This one has t sub 0.1. We've seen this before with z's. Remember that this is telling you that this is the area down here and that you're finding the t value with this area to the right. So t-score with area equals 0.1 to the right. That's what this is telling us right here. When we see this guy, this is telling, look for the t-score with an area of 0.1 to the right. So just like before, I'm going to draw my little distribution here. I'm going to have 0 in the middle, because that's the middle. I'm looking for one that has 0.1 to the right. So remember that there's 50% to the right of 0. So 0.1 is less than 50. That's only like 10%. So it's going to be over here. And it's got this area here, and this area is going to be 0.1 or 10%. And we're looking for that t-score because it has to have 1% to the right. It's not to the left because this one is to the left, but this one, when you write it this way, means to the right. Okay, so we're looking for this t-score with that correspondence, but we do also need to know degrees of freedom. That's the big thing with t-scores. You also have to know the degrees of freedom. Here they give us n. They say n is 18. So the degrees of freedom would be 18 minus 1, because it's always one less. So the degrees of freedom would be 17. So we'll use the 17 degrees of freedom. We use 0.1 and the one tail. And again, there's only one tail. There's not two. It's just the right side. And that will give it us off the chart. So we're going to find the 0.1, and one tail. We're going to find our 17 degrees of freedom. So we got 17 degrees of freedom, 0.1 and one tail. So I go to the right, I come down, and we see that the answer for this one is 1.333 because it's 17 degrees of freedom, and it's 0.1 and one tail, so 1.333. So the t-score is 1.333. Now on the last one, we kind of almost missed the negative, so we have to watch the negative on this one. Well, no, this time t-score is on the right, so this t is positive. You don't have to worry about a negative on this one. So 1.33 is done. So you kind of notice with the chart, the chart's really giving you the scores on this side. It's not giving you the t-scores on the left side. That's when they do that because a lot of times that's what we want, is we want the ones on the right side. But you got to be really careful with that. Okay, let's do another one. So here they give us the area of 0.05 to left. So area of 0.05 left of negative t, and area of 0.05 right of t. So they actually have two different t values. And we're trying to find, and they say n is 37. So first off, we know right from this that the degrees of freedom is one less. The degrees of freedom is 36, right? Because the degrees of freedom are always one less. I draw this distribution, right? So I have 0.05, so 0.05 to the left. So this one's going to be 0.05. And I have 0.05 to the right. This is going to be 0.05. Remember, because there's 0 in the middle, this has a nice symmetry. And so this one is going to be negative t, and this one's going to be positive t, and they're going to be the same value, only one's going to be negative, one's going to be positive. So we combine either one of those values and we're good to go. So we could either do t with 0.05 to the right, or negative t with 0.05 to the left, and again, the degrees of freedom 36, that would be good. So let's do that. Let's do that with 0.05 to the right, so just one tail has 0.05, 0.05, one tail, and degrees of freedom 36. So notice this one only goes down to 27 on this side, but that's because it starts back up again over here. So we go over here by 36. So there's our 36 right there. And then we want 0.05 and one tail. So in one tail, we want 0.05. So we got a 0.05 and one tail, and 36. So we come down and come over until we hit this one is 1.6888, or sorry, 688. That would be a value because it has the right degrees of freedom, 36. and 0.05 in just the one tail. So t is 1.688. So what's negative t? Well, it's just the negative version, right? So negative t would be negative 1.688. Now, you did see on the chart, it does have stuff for two tails. So on a problem like this, you could use two tails. And so if you combine those two tails and see that there's 5% there, 5% there, there's a total of 10%, or 0.1, you could have used the two tails with 10%. And you'll notice that's the same exact columns as the one tail with 5%. So that's why it didn't really matter which one I did, right? Because one tail of 5% would combine for two tails of 10%. And either way, you're going to get the same 1.688. So even if you use 10% in both tails, the total, or 5% in one tail, either way, you get the same number. So that doesn't really matter on that. Okay, so those would be the values, for t and negative 2. Let's do one more. Now I want t of alpha over 2 for a 90% confidence level. Remember the 90% confidence level, that's going to look like this, where the middle piece is going to be 90%. So 0.90 is the middle piece. That means there's 10% left to split between the two halves, right? So you have 10% in the two tails. So alpha would be 0.1. But we put half in each tail, so we're going to cut that in half. We're going to have 0.05 in one tail and 0.05 in the other tail. So we split it between the two tails. So this one is actually very similar, right? The same 0.05, 0.05. The difference here is now the degrees of freedom are changed because the sample size changed. This sample size is 45, so the degrees of freedom of this one would be 44. I have 44 for the degrees of freedom. So I go to my chart and say, okay, I'm doing 0.05 again, because that's the same. So I'm doing degrees of freedom 44. So I go on here and I look and I say, wait, 40, 45, there is no 44. So you can get a rough estimate by getting close, and the closest you can get to 44 is 45. So you could do that, and then do 0.05 in one tail, and you could say, well, close estimate would be about 1.679. And for some case situations, that might be good enough. But there is a way to get a better answer, and that is your calculator. So t-scores, you can actually find t-scores with your calculator, just like you can find z-scores with your calculator. So we're going to do this. We're actually going to use the calculator because that's going to give us a better answer since the degrees of freedom isn't on our chart. And you could use this for all the 30 previous problems too. So to do the calculator, we're going to do that second button in the distribution, just like we did z-scores. We're going to do the same thing. And we're going to use, instead of inverse norm, which was for z-scores, we're going to use inverse t, which makes sense, right? Inverse t for t-scores. So we're going to use inverse t. Hit enter, and it's going to need two things. It's going to need the area and the degrees of freedom. So I'm going to give the area. Notice that the area is 0.05, right? So the area, 0.05, area. And then the degrees of freedom. So I'm going to put 0.05, and then the degrees of freedom. So the degrees of freedom in this case was 44. So 44 is my degrees of freedom. Put that in, hit enter. Again, you might have to type it like this in your calculator. You just get the inverse t and type 0.05 and then 44. And it'll give us the value. So we get negative 1.680. You can see that's not quite what we got before when we were trying to use the estimate. We said, okay, at 45 and 0.05, we got 1.679. So this is 6.8. So it's a little bit bigger. It also has the wrong sign because when you do this, this is actually doing area to the left. So it actually found this t-score. It found the negative t. If you want the positive t, of course, you just turn this into a positive number. Since t of alpha over 2 is this one, right? Alpha over 2 is the one with 0.05 to the right. That's what we want. We actually want the positive one. So this is the positive, not the negative. If they wanted the negative, they would put a negative in front of it. It would have to be negative t alpha over 2. And so if you put negative 1.6 in this one, you get it wrong. And you might get it wrong if you put 1.679, because that is a little bit of rounding. It just depends on how much room for rounding MyStatLab allows. So that's one reason why you might want to use the calculator if you're using it when your chart doesn't work. Also, if you just want to get comfortable and use the calculator for every t-score, that's fine. It's always a good idea still to draw your chart so you think about what's going on. Notice that you always need the degrees of freedom when doing t-scores, so you know what your sample size is so you can find degrees of freedom. But they're similar to z-scores. There are a lot of similarities, just a little more work because you have to find those degrees of freedom to figure them out. So they vary a little bit from problem to problem. Okay, so So now we know about t-scores. We're ready to use those because we will use those as critical values when we're working with means. So we're doing problems with means, not proportions like last time, but means now. We will use t-scores instead of z-scores. We are going to use those t-scores as our critical values. So to make our confidence intervals just like last time, we're going to find critical values. So we'll need to find the critical values. They will depend on the confidence level and the sample size because of degrees of freedom. And then we'll take the critical values and find the margin of error. Remember that the formula for margin of error will use critical values. And then once we have the margin of error, we'll find the endpoints of the confidence interval because we'll take the point estimate, so the sample mean, and add subtract to get the confidence interval. So critical values, you'll use the calculator most likely. I'll show you how to do that a few times as we go. Once you get the critical values, and it will depend mostly on this, confidence level and the sample size, which is the difference because before all you needed was the confidence level when you're doing z-scores. With these t-scores, you also need the sample size. Margin of error has a formula just like before. This is the formula for margin of error. It does depend on the critical value, right? So that's your critical value based on your sample size and your confidence level. The sample standard deviation, so S is the sample standard deviation, so you have to know that. And then N, of course, is the sample size, like always. So use that calculation and you'll find the margin of error. So that's what we'll do first. We'll go ahead and actually find the critical values and the margin of error, and then work our confidence level here as we go. Okay, so first off, sample of 17 students. So that is N, right? So N is 17. They have an average age of 21. So this is an average age. This is the sample mean, right? Sample mean is the average of your sample. So they took a sample, found the average of the sample, says 21. Has a standard deviation of 3 years, right? So that's 3 is the standard deviation. That is going to be your sample standard deviation. So again, we're working with sample. These are all sample values. They want to find the margin of error, so we're looking for the margin of error for a study using a 90% confidence level. So first off, I got to think about it. If I'm doing a 90% confidence level, I'm doing my distribution. I've got 90% in the middle, right, 0.9. Got 0.1 to split between the two sides, so both sides end up being 0.05. We've seen this before, right? We just did this twice on the last page. We're looking for those t-scores. We're looking for the critical value. We're looking for t of alpha over 2. Where the alpha over 2 is this 0.05. We're looking for that. To do this, we do need to know the degrees of freedom. So note that since there are 17 in the sample, the degrees of freedom are 16, right? Always one less than 17, the sample size, right? So this is 16 degrees of freedom. So if I do that inverse t, and we plug in the percentage area we're looking at, so we're looking at 0.05, because each tail is 0.05, and the degrees of freedom, which is 16, that'll tell us what it is. So we can do second distribution inverse t, and put 0.05, which is already in there, so we leave it. Degrees of freedom is 16, paste it in here. Again, this is going to give us the negative number. We want the positive, so we're going to take that and get positive 1.75 if you want to round it, or 4.6. It just depends on how much you want to round it. 7, I'll do 1.75. I'm rounding more than I probably normally do. That's fine. So that's our degrees of freedom. That's our critical value using the degrees of freedom in our area. That's our critical value. This is t of alpha over 2. We wanted the positive one because you use the positive number when you're finding margin of error. Margin of error should never be negative. So if you use the negative number, you get a negative margin of error. And you don't want a negative margin of error because margin of error is how much room you want. So you want a positive amount of room. So we'll use this value. So margin of error, that's our first value, is 1.75 times the standard deviation, which they gave us is 3. So we put 3 on the top. And then square root of sample size. So on the bottom we'll have square root of 17. So once you have the critical value, the rest of it's pretty easy. But again, you have to find the critical value every single time. There's no chart with t-score critical values because the degrees of freedom changes every time. So the critical value changes every time. So you have to find these yourself. And thankfully the inverse t makes that pretty easy because all you have to do is figure out the 0.05 and the 16. They didn't tell us the 0.05. We used the 90% confidence level to figure out there's 0.9 in the middle. So there's half the 0.05 in each half. 90% in the middle, then there's 5% on each side. And that's how we figure out the 0.05. And then the 16 comes from the sample size, gives us the degrees of freedom. Okay, let's put that in and see what you get. So we got 1.75, 1.75 times 3 is our standard deviation, divided by second square root of 17. Oh, that's right, yeah, 17. I'm looking at this for you. 17. I almost thought I did it wrong for a second. been a year since we did this. Okay, so we got the sample size 17, we got the standard deviation 3, we got the 1.75. We put in there, we get 1.27, and that is our margin of error. So the margin of error for this one is 1.27. Not huge. So I guess, that might be big considering that, 21 years is the age. So you could go up 1.2 years or down 1.2 years. And this is years because now we're doing a mean. So we're not looking at percentages anymore. We're looking at like what is the average, and this is the average age or average years age. And the standard deviation is years. So this mean is also in years. Or this error is also in years. So that would be our error for that problem. So remember, when we do constant intervals and stuff, we, from the last section, same thing here. We take that error at 1.27 years and say, okay, we got a 21 from our sample, but we have to allow for some wiggle room. So it might be up or down from that, like a 1.2 years, up above that or below that. So if someone said 22 or 20, I'm going to say, okay, that's probably reasonable because I got 21, but I have a year and some worth of wiggle room I need. Okay, so that's margin of error using the critical value to find the margin of error. Okay, let's try another one. Here we have a sample of 35 students. They have a mean of 115 pounds, so that's average. Sample is n, mean is x bar, your sample average. Standard deviation of 25 pounds, so that's going to be your sample standard deviation s. That'll be the margin of error, so again we're looking for margin of error for a 99% confidence interval. So we're doing 99%. So when I do my distribution this time, I'm actually putting 99%, so 0.99 in the middle. That means I only have 0.01 left between these two halves. So if I split that in half, I actually end up with 0.005. This is actually 0.5%. Because if you have 99% in the middle, you only have 1% left, so you only have half a percent each side. So you have 0.005 on both sides. Again, I'm looking for this t of alpha over 2. Alpha over 2 in this case is the 0.005, right? That's alpha over 2. So we're looking for the t-score of 0.005. Now, to find t-scores, we also need to know the degrees of freedom. So note, hopefully, that you saw this, that degrees of freedom is 34, right? 1 less than 35, so degrees of freedom is 34. So we're going to do inverse t with that 0.005. Again, bigger, percentage in the middle means less down here in the end, and the 34 degrees of freedom. So I'll do my inverse t, so I'm going to do second distribution, inverse t, there it is. I have been my 0.005, 34 degrees freedom, and we get our answer, which is negative 2.7. Again, we want the positive value, so we're just going to turn this to positive numbers. So that's the nice thing. You don't have to really worry about the 0.005 giving you a negative, because you can always know that's just this value they gave you, and you just can turn it to a positive to get this value, because it has that nice symmetry. So we'll just actually turn this into 2.728. So even though it feels weird because we keep getting these like negative numbers here from the inverse t, it's really giving us this number, and because of symmetry, we know that these are the same. The only difference is this one's positive, that one's negative. So we're just going to take the positive version, even though they gave us the negative version. That's the nice thing about the fact that the zero's in the middle here, and it has a nice symmetry. So we can just take the number and flip the sign. And we're doing t-scores like this. Okay, do margin of error again. So margin of error, again, we use that same formula. We find the t-score we just found, so 2.728. Multiply by the sample size s, which is 25, so 25 on the top, over the square root of n, which is the, sorry, I said sample size. Standard deviation, that's the standard deviation. I don't know where sample size came from. Standard deviation, n is the sample size, which goes on the bottom underneath the square root. So standard deviation on top, the sample size on the bottom. So you end up with the 25 standard deviation, the 35 sample size, and that's what we're going to plug in. Okay, so we're going to do 2.728 times 25 divided by the square root of 35. And that's our margin of error. So the margin of error, this one is actually 11.5. It's way bigger margin of error, but you notice that the mean here is actually 115, and the standard deviation is 25. And so we actually have a lot bigger spread here. So even though this is a lot bigger margin of error, it's actually not that big of a deal, because now we're talking about pounds, not years. We're talking about like 25-pound spread versus 3-year spread. So this looks maybe like it's a lot worse, but it's actually probably not that bad when your standard deviation is 25 and stuff. This is a lot smaller than that. So, but that's the margin of error. So again, we would look at that 150 pounds and say, well, that was what we got from our sample. In real life, the number could be anywhere to like 11.5 pounds above that or 11.5 pounds below that. So within that range, if you say like 120 pounds or 110 pounds, I'm probably going to say that sounds okay to me because that's close enough to my 115. As long as it's within like 11.5 pounds, we're probably going to call it good. One other thing to note about these, so we talked about the requirements. I want to just see if you guys notice this. Note that this one satisfies the normality requirements because the sample size is big enough. So here, n equals 35, which is bigger than 30. So we have a large enough sample. So here we wouldn't even have to worry about if the information was normal or if there's outliers. The previous one, however, only had 17. So this one, note, n is equal to 17, which is less than 30. So to do this problem, we actually have to require that either the data is normal, or sorry, the data is normal and there's no outliers. So we would need, roughly normal and no outliers. Now, I'm not really going to worry about that too much. An advanced stats course, I could probably be more nitpicky about that, but we're just doing basics, so I'm not going to worry too much about that. But that's something you would actually do if you have real statistics. You say, oh, I only took the sample 17. I'd look at the data, make sure there's no outliers, it's roughly normal, before I even tried to do any of this, like finding the margin of error and confidence level. Okay, so now we know how to find the margin of error. We talked about how to find the critical values. Now let's go ahead and actually build some confidence intervals. So to do confidence intervals, it's very similar. We're going to take our point estimate, which in this case is x bar, that's our point estimate, so the sample mean, and we're going to add and subtract the margin of error, e, and that will give the endpoints of the confidence interval. So you can do it all three ways. You can do it with the plus or minus like we saw last time. You can do it this way where you put the mean in the middle and then say it's going to be bigger than the bottom value and less than the middle value. People like to write it this way because then you can see the point estimate and the confidence interval. I tend to probably write it this way. So that's probably the way I mostly will write it. So I'll subtract and find the lowest point, add and find the highest point, and just give you those two endpoints. So that's mostly what I'll do. So let's go ahead and do that. So in a recent study, a survey of 25, so that's how many people were surveyed. So that's going to be our sample size n. Gave a mean value of 23 pounds lost. So that's going to be our mean. So that's going to be x bar, our sample mean. Sample standard deviation of 8 pounds, so that's our standard deviation. So this is going to be S, the sample standard deviation. We want a 95% confidence interval, so this means that our confidence level is 95%. So when we do our confidence distribution kind of thing, we're thinking that in the middle here we have 0.95. Now to find critical values like we've been doing, remember that we're going to take this and we're going to say, oh, critical values, well, there's 95% in the middle, there's 5% between the two halves, so they end up being like 2.5%, so 0.025 in both the tails. And so if you wanted to find the critical value, you'd do inverse t of 0.025. And then the degrees of freedom. What's the degrees of freedom? Well, because there's 25 sampled, degrees of freedom is going to be 24, right? Because it's one less than the number sampled, so 24. And that would give you your critical value. So if you want your critical value, you do that. So I'm going to clear this out just next to me. So the second distribution, inverse t, 0.025, because that's 2.5%. Degrees freedom is 24. Put it in there. It's going to give me the negative, but I'm going to turn it into a positive again. So my critical value would be 2.064. That's my t-score that I found here, alpha over 2. This is alpha over 2. I could use my margin of error formula, where I take the t-score I just found, 2.064, times the sample standard deviation, which is 8 pounds, over the square root of the sample size, so square root of 25. And this would get the margin of error. So I'd do 2.064 times 8 divided by square root of 25. And we get a margin of error of 3.3. I'm going to shrunk to 3.3. So to build a confidence interval, we're going to take our point estimate. Remember the point estimate is the x bar. So the point estimate equals the x bar is 23 pounds. So we're going to add and subtract. We're going to take that, we're going to add and subtract this 3.3. And that's how we're going to get our margin of error. So if I take and I subtract 3.3, so 23 minus 3.3, think I get 19.7. If I do 23 and I add 3.3, I get 26.3. And that would be my confidence interval. Again, the point estimate, the mean, the sample value, should be in the middle. So 23 should be right here in the middle. And then you should have 3.3 up and 3.3 down. And this is your wiggle room. So you are 95% confident, because we did a 95% confident level. We're 95% sure that the real average, the average for the entire population, not just for the sample we took, but the whole population, is going to be in this window. We're 95% sure it's somewhere in there. We don't know if it's closer to 26, closer to 19, but we're 95% sure it's somewhere in that window. Yeah, we got 23 from our sample, but we're looking at this window and saying it's 95% sure it's somewhere in there. It's in that range. Again, if you want this window to be smaller, take a bigger sample. That makes the window smaller. Also, you can maybe not worry about so much confidence. If you do like 90% confidence, the window gets smaller. If you want a bigger window, if you want a bigger, I don't know why you want a bigger window. Maybe you want to be more confident though. If you go more confident, the window gets bigger. But that's the confidence interval. This one. Again, this is for means, not for proportions. So not percentages, these are actually pounds, right? So this is somewhere between 19.7 pounds and 26.3 pounds. Because this is weights, because that's what we're looking at, the average weights. Okay, let's do one more. They want us to find the 90% confidence interval. They give us the degrees of freedom, mean, sample standard deviation, or so sample standard deviation, all that stuff. So again, we can do the same thing we just did. Build our chart, put our 90% in the middle, so 0.9 in the middle, which means we have 10% left, so 0.05 or 5% per half, right? Because if you take up your 10%, split it in half. So find our t-score again. So again, I go to my inverse t, and I put in that area of 0.05 and the degrees of freedom, which this time they actually gave them to us. This one's one you got to really notice here. They gave you the degrees of freedom 15. They didn't give you the sample size. So it's really tempting to maybe put 14 down here because we've been subtracting 1 every time. But notice that this is actually the degrees of freedom, not the sample size. So we're just going to go ahead and put that in because that's what we want. We want the degrees of freedom here, not the sample size. So that's actually already the number we want. So plug that in. We'll do our second distribution, inverse t, 0.05 for the area, 15 for the degrees of freedom, and we get 1.753. Again, we're going to leave this as positive because we want the positive value. Find our margin of error, because it does ask you to find the margin of error, so we're getting that. Use that 1.753. Remember the formula has the standard deviation and the square root of the sample size. So standard deviation is 12.2, so 12.2 goes on top. Square root of the sample size. Now here's where you got to be careful. Notice they didn't give us sample size. They didn't give us n. But we know because the degrees of freedom is 15, the n is going to be 1 more, right? Because it's going the other direction. So this is 16, so we only want the square root of 16 down there. But I know they do this on the homework, and I think they just do this to see if they can trick people, because people are so used to getting the sample size instead of the degrees of freedom. So they kind of did it backwards on this one. So just stop and think, oh wait, that's the smaller number, so the sample size is always the bigger number. Okay, so that will give us a margin of error. So I'll do 1.753 times 12.2 for my sample standard deviation, divided by the square root of 16. And, oops, I just typed it in twice. So I get 5.35. I'm going to go down to there, 5.35. That's our margin of error. That's how much margin of error we do. Again, to get the confidence interval, so I want to make the confidence interval, we take the sample mean, that's our point estimate, right? Because the mean, that's the average from our sample. That's our estimate, what we think it's going to be. And we take that value, we subtract the margin of error to get the smaller value, so subtract 5.35. And we do that value, we add 5.35 to get the higher value, so 42.5 plus 5.35. So subtract and add to get the 2 low and high spots. So what is, I don't want to do this in my head, so maybe 42.5 minus 5.35. 37.15 would be the low value, and the high value is going to be 47.85, and that would be our confidence interval. So even though 42.5 is what we got from our sample, we're going to say, well, it's going to be somewhere in this range. We are 90% sure that it's somewhere between these two numbers. Again, you get a smaller margin of error because you had a lower confidence interval, even though we had a really small sample size of only like 16 people. So that's the idea. Now all this, you can do with a calculator. You don't have to do this by hand. So if you want to do this with a calculator, there is an operation on your calculator. If you go to the stats option and the tests, this is where we did the confidence intervals last time, same place. There's confidence intervals here. But when you do this, instead of doing a z interval like we did last time, we're going to do a t interval. We're doing the t intervals with means because we don't know the sigma, standard deviation for the whole population. So we're going to use 8, which is our t interval. So we'll do a t interval. So on the calculator, we'll do a t interval. You actually have to type a lot of numbers in here. First, you have to put that we're going to do the stats, not the data. So this, you use the data, and someone actually gave you the results. So they went out and did their survey of like 15 people, and they just gave you the data without calculating like the averages and stuff. You can do that with data. We're going to do the stats because we actually know like what the average is, what standard deviation is. So we put in the standard deviation, the average first, which is going to be that 42.5. So we put in 42.5. So we put X bar first. And the standard deviation, which is 12.2. That's your sample standard deviation. So 42.5, 12.2. The n, which is your sample size. So in this case, it was 16. So put n for 16. And then the confidence level. So this would be 0.9. And that's the C level. And that will give us our t interval. So all that in the t interval is 37.153 to 47.847. And that's the same thing we got over here. So you can see it got the same value. This one just is rounded less, right? Ours is rounded more. So you can do it by hand, or of course, you can just use the t interval on your calculator. So that's what I'll do from here on out, because honestly, I think that's easier than doing all this process. You'll notice it does not give you the margin of error. So if you want to do the margin of error, you do have to figure that out. But it does give you, the interval. That's really what you want in this case. It's like the interval most of the time. So if you want the margin of error, remember, there is a way to get that, which I believe is on the last page right here. And we see it because we did the same thing last week. We said that if you have the two parts of the interval, you can find the point estimate by adding and dividing by 2. And you can find the margin of error by subtracting to find the distance and dividing by 2. So that's the trick. So we'll use the calculator 9 times out of 10. And then if we want the point error, the estimate, the margin of error, we'll just use this formula for the margin of error. The point estimate, again, if you don't know what the point estimate is, it is the middle number in your confidence interval. So you can always add them up, divide by 2, and find that middle number. So that's the trick for finding these from the confidence interval. So if all you have is the confidence interval, you can do this information. Or even if you are doing a problem like this one, and they ask for both the confidence interval and the margin of error, you could skip this whole process of finding the margin of error. You could just get the confidence interval, subtract the two numbers, divide by 2, and you'll get that 5.35 margin of error. Okay, so let's do a couple examples to show you what I mean. So say you look it up in this magazine journal financial study, and they tell you that the average yearly college costs are $25,000 to $55,000. So this is an average, this is a mean, and because they give you a range, they really just gave you the confidence interval. They want you to find the point estimate and the margin of error. So to find these, remember the first thing we're going to do to find the margin of error, the point estimate, X bar, we're going to add the two numbers and divide by 2. So we're going to take the 25,000 and add the 55,000 and divide by 2. And that'll give us the middle, which is the point estimate, which is the average they actually got from their sample. So we're going to take the 25,000 plus the 55,000, divide it by 2. And we see that what they got from the sample is they actually got 40,000. So they did this survey, did a study, and they got 40,000 for their average from their sample. And then they built the confidence interval and said, okay, well, if you expand it out, you end up with this whole range. So they had to find the margin of error to do that. So the margin of error, again, we're going to subtract them because we're finding how far apart they are, and then divide by the 2 because half the distance is your margin of error. So we're going to take the big number, 55,000. That's a small number, 25,000. And then divide that by 2. Well, 55,000 minus 25,000 is actually 30,000. And 30,000 divided by 2 is 15,000. And that should work because you should be able to take this number and add and subtract it from this number to get the interval, right? Because you take the middle number, add and subtract your error, and you get the confidence interval. So 40,000 plus 15,000 is 55. 40,000 minus 15,000 is 25. So yeah, it looks like we got the right numbers. So that's what you could do. If you have the confidence interval and you don't want to do the margin of error the hard way, you can just subtract the interval, divide by 2, and that's one way to get your margin of error. Let's do one more like this, but the same idea. They're going to give us the range, which is 72.4 to 78.6. That's our range. To find the mean, we add those. So I'm going to say 72.4 plus 78.6, and then divide by 2. So divide this, so 72.4 plus 78.6, and divide by 2. We'll get 75.5. So that would be the middle. That's the number they got when they did the study. They got 75.5. And then to find the margin of error, we would take the numbers and we'd subtract them. So we'd do 78.6 minus 72.4, and then divide by 2. So 78.6 minus 72.4. You get 6.2, divide that by 2, because I only want to get half. So the margin of error is 3.1%. That's the margin of error. And that's it for this section. So now you know about finding confidence intervals. And confidence intervals are really important. We're actually going to use them the rest of the semester. We already talked a little bit how they can be used for testing claims, which is actually what chapter 8 gets into, is testing claims. So we'll use them in that chapter, and we'll use them later on in the semester. It's just a great way to take your estimate, your sample result, and try and extrapolate things about the entire set, about everything. So that's why we like these confidence intervals. And again, you have to build the margin of error and then add and subtract from the point estimate. Thankfully, you can make the calculator do all that for you, but it's very good to know what it's doing. It's taking the sample mean, this average sample mean, and adding, subtracting this margin of error to build the confidence interval. All right, so that's it for this set. So I'll see you on the next.